and it wasn't until 1945 that it was revealed to contain Pythagorean triples. Subsequently, it has become one of the most studied objects from the ancient world.
A cracked clay tablet sat ignored for a century, until AI read it like a code. What looked like a dusty list of numbers turned out to be a message from 1800 BC, written in wedge marks so precise they shouldn't exist. You'll see how a palm-sized artifact, Plimpton 322, rewrites math history and exposes a system of power older and colder than we imagined. Archival trails, field tablets, and exact ratios decoded by modern AI. We'll trace the discovery, decode the numbers, reveal their uses, follow the researcher who connected the dots, and confront why the why is the most chilling part. From dust to dread. At first glance, Plimpton 322 looks ordinary, even dull. A palm-sized rectangle of cracked clay, its surface faded by millennia in the earth, it could easily be mistaken for a fragment of an ancient shopping list. And for decades, that is precisely how scholars treated it. Dug up in Mesopotamia in the early 1900s, the tablet passed quietly through the hands of a roguish archaeologist named Edgar Banks, a man whose flair for adventure
Plimpton 322, found in the desert of Iraq around 1920.
Later inspired the fictional Indiana Jones. Banks sold the artifact to a wealthy New York publisher named George Arthur Plimpton, who collected rare educational curiosities. After Plimpton's death, the clay piece was donated to Columbia University and tucked away in the mathematics department. There it sat locked behind glass, catalogued with the sterile label Plimpton 322. No fanfare, no mystery, just another relic in a growing archive. For most visitors, it was little more than a curiosity, a lump of clay that seemed far too humble to matter. Strange stares were drawn toward the tablet even in those early years. Some scholars noted the jagged left-hand edge, where a section of clay had broken away. The breakage looked almost unnatural, as if that corner had been deliberately torn off. Was it the wear of time, or at some point had something intentional happened? That broken edge would later trouble the minds of researchers and fuel the speculation that this tablet is only part of a larger, more complete work. If that is true, then this missing portion may have contained the very instructions to decipher the rest of the tablet's secrets. The festive style survived 4 columns and 15 rows of wedge-shaped markings, cuneiform numbers in Babylon's base 60 system. To an untutored gaze, these look like any other list, tallies for goods, grain delivery, or trade exchange. But they had a problem. The numbers were too huge, outstripping any reasonable estimate for numbers of sheep, barley, or silver. They were not round estimates. Instead, they were very precise, deliberate, and somehow strangely ordered. The consensus among academics for years was indifference. Some claimed it was a merchant's ledger. Others proposed it was a math exercise for the scribe. The most charitable interpretation entailed the consideration that it might have been a teaching tool. However, this, too, does not help explain the precision. Lacking context, the observations were stored in the lecturing system, while the tablet stood gathering dust. Generations of students marched past the display case, oblivious to the existence of something so extraordinary that it was just an inch away. The disquiet persisted. What made the numbers so cleanly arranged? Why was each row supposed to stand in connection with the next? And what was on the edge of something now lost? Such questions flickered at the edges of scholarly articles, but could never find their way into more mainstream ones. For most historians, then, Plimpton 322 remained a misfit, an artifact recognized but not understood. The great irony is that the most significant clue was staring right into their eyes. The sequence of numbers was too precise to be random. It was almost as if the tablet held a code, waiting for the right kind of tools to discover its pattern. Only in this age of digital imaging and artificial intelligence, that pattern finally come to light, and it would be quite a shocking revelation. This was something other than just a ledger or an exercise. It was something much farther advanced. The odd part wasn't the clay, it was the pattern that refused to be ordinary. Numbers that shouldn't exist. When modern scholars began looking more closely at Plimpton 322, They realized the numbers on its surface weren't random at all. They weren't lists of goods, nor the results of routine bookkeeping. They followed a precise mathematical pattern, one so clean it seemed impossible for a civilization as ancient as Babylon to have produced it. The tablet records sets of 3 numbers. To a modern eye trained in geometry, they are instantly recognizable: Pythagorean triples. These are whole number sets that satisfy the equation most of us learn in school: A2 plus B2 equals sine C2. The classic classroom example is the 3-4-5 triangle, where 3 squared plus 4 squared equals 5 squared. But Plimpton 322 didn't stop at simple, small sets.
This makes Plimpton 322 a powerful tool that could have been used for surveying fields.
It listed enormous triples with flawless accuracy. There are some examples. The most striking is the 4th row, where the numbers are 12,709, 13,500 and 18,541. Squared and checked, they do fit perfectly into the equation. Not rounded, not approximate. All exact in just real numbers, unmatched in the precision by the outside world, like a solved puzzle. Whoever engraved these numbers in clay was not just tossing in theories. They understood how right angles connected with each other, with an understanding not at all supposed until more than a millennium later. As much as the history of mathematics has been taught, there would be a theorem discovered in Greece in the 6th century, before the Common Era. It was Pythagoras himself, the philosopher and mathematician, who gave it its final form. What is surprising, however, is to find it here inscribed in Babylonian clay tablets dated to about 1800 BC, thus proving that the Babylonians had possessed this principle many centuries before Pythagoras was ever born. These implications are indeed enormous. It is not a matter of coincidence or chance. The tablet displays not 1 or 2 isolated instances of right-angled triangles. It shows an explicit series, each row progressing from steep ratios to shallow ones in a very systematic way, as though it is a reference chart. Such ordering suggests practical use, and not mere theoretical musings. It was a tool aimed at being consulted, not merely something to be gazed at. Equally important is the numerical system involved. The Babylonians worked in base 60, such is the sexagesimal system. Unlike our base 10 decimal, bases 60 divide neatly into a whole bunch of factors. That meant fractions could be expressed extremely accurately, without all the hassle associated with rounding out in contemporary mathematics. Almost as stunning to modern scholars as were the triples was the realization that, in many cases, the Babylonian system was not just advanced, it was superior to the Greek trigonometry that would be. Even more troubling to scholars was the lack of errors. Old records usually exhibit a few small imperfections, some corrections or inconsistencies, indicating that writing was done manually and adjustments were made. There isn't any mistake left on Plimpton 322. Each row, each number is perfect, as though copied from a perfectly established system. This was not the work in progress of a civilization that was still getting itself to come to terms with advanced mathematics. For centuries, the broken edge of the tablet has been taunting academia, but survived the numbers, and the tale alone changed reality for a long time. If Babylon had a more accurate trigonometry than Greece, the rewrite is quite different from history itself. The troubling questioning became clearer. What else had they known that we had forgotten? If the math is perfect, the better question is who needed perfection, and for what? Tools of power, not theory. If Plimpton 322 were nothing more than an academic curiosity, it would still be astonishing. But the evidence suggests it wasn't theory at all. It was a working tool. Its sequence of Pythagorean triples wasn't recorded to impress future generations. It was created for immediate
of rectangles, which have very pleasant, easy to manage measurements. These are called the Pythagorean triples.
Practical use in a world where mathematics wasn't abstract, but woven into power, law, and architecture. Babylon was not a city of modest huts and winding dirt paths. It was a hub of monumental engineering. Towering ziggurats pierced the skyline. Irrigation canals crisscrossed the plains, and massive temple complexes dominated civic life. These projects demanded exact geometry. Angles had to be perfect, foundations had to be level. Without precise ratios, walls leaned, towers collapsed, and canals flooded. Plimpton, 322, provided a quick reference chart that could deliver flawless right angles every time, something a builder, surveyor, or architect could rely on in the field. This discovery of a new artifact, 427, has confirmed that practical role. Retrieved from the archives of Istanbul's Museum of the Ancient Orient, Psi.427 is a surveying map about 3,700 years old. Its clay surface shows lands measured up accurately in the same types of Pythagorean triples as those found on Plimpton 322. This was not abstract mathematics. It was applied geometry to resolve land disputes. Straight lines and corners set true allowed the Babylonians to enforce boundaries with a serious claim. In a society where ownership of land determined wealth, survival, and status, they were not simple tools. They may even be political weapons. Consider a society where the outcome of a legal dispute wasn't decided by a court, but rather by a tablet of numbers. If boundary lines were crossed according to the ratio numbers, there was nothing to debate about. The truth, according to the numbers, dictated all. It was a bypass to emotion, compromise, and even corruption. Cold, absolute, final. That way, Plimpton 322 was not per se a mathematical artifact. It was, by its definition, an empowerment document, allowing rulers and elites to impose decisions under the auspices of numbers. Another theory puts forward the argument that Plimpton 322 belonged to some elite education system. Scribes and administrators in Babylon studied in a specialized school, where not just the art of writing, but also the field of mathematics were closely controlled. The students of such an institution would hardly consider something as Plimpton 322 as interesting. They used to measure and create ratios as to governance rather than sheer curiosity. They would be the ones later managing vast irrigation networks, supervising temple construction, or adjudicating in difficult disputes. In this case, the tablet was not just a tool, but rather a training manual for the ruling class of the empire. The collected evidence evokes grim extrapolations. Mathematics in Babylon was hardly a static pursuit within scrolls and onto classroom walls. It hammered into the very structure of governance, construction, and the coercive aspects of society. Plimpton 322 might have been a condensed manual enabling the few to husband resources, resolve disputes, and erect monuments that awe and subjugate the masses. They gave precision not as a right, but as a source of power. Again, this knowledge notwithstanding, there was a growing sense in the scholars that something else was involved. Plimpton 322 did not seem to hang together. Its broken edge seemed to suggest any number of additional columns that might have held instructions or even definitions of relations much more complicated. If what has survived were already a template for hegemony, what was missing might truly indicate an even more wondrous power. When numbers make the rules, someone gets to hold the ruler. The researcher who wouldn't blink. For most of the 20th century, Plimpton 322 was little more than an academic puzzle. Strange, yes, but not urgent. That changed when a mathematician in Sydney decided he couldn't ignore it. Dr. Daniel Mansfield was not an archaeologist, not a treasure hunter, but a lecturer preparing coursework for his students. What began as an ordinary search for teaching material turned into a career-defining obsession.
This tablet SI427 shows us that the application is actually surveying. These people are making bound.
Mansfield first encountered Plimpton 322 in photographs. To most people, the faded wedge marks would look like meaningless scratches, but he saw order. The numbers weren't only large and deliberate, they sang with precision. To him, the tablet wasn't broken trivia, but a carefully crafted instrument. He began to dig deeper, figuratively at first, reading decades of neglected academic papers, piecing together the hints left by earlier scholars. In 2017, his collaboration with Professor Norman Wildberger concluded with a brave claim that the Babylonians had developed trigonometry 1,000 years older than the Greeks. Different from Greek trigonometry, based on angles and degrees, the Babylonian system was based on ratios expressed in base 60. Hence, it avoided the rounding errors that plagued Greek methods and even provided cleaner calculations than many modern-day ones. Mansfield and Wildberger published their findings with the shimmering title, Plimpton 322 is Babylonian exact sexagesimal trigonometry. The academic community stirred. Should their conclusions be correct, a rewriting of the history of mathematics was to begin. Pythagoras could no longer remain the discoverer. Instead, secretive Babylonian scribes must have known the same exact principles with an unsettlingly modern-day flair. The Plimpton 322, he suspected, wasn't the only gem of the culture. At one stage or the other, it must have been accommodated in a broader kit, dealing with different areas of governance and construction. To prove his point, he set out to trace slight trails in excavation records and museum archives. This searching led him to another tablet that is now referred to by the inventory number Psi.427, a dusty relic catalogued decades before and pretty much forgotten. In 2019, Mansfield found himself at Istanbul's Museum of the Ancient Orient with the clay map held in his hands. One more fine catalogued piece of land surveying in the field was C.427, illustrating the application of Pythagorean triples for precisely marking property boundaries. Far from simply a pure academic endeavor, it was a practical science geometry for resolving disputes and managing resources. Thus, Plimpton 322 and Psi.427 formed a matched pair, one laying out the ratios and the other actually demonstrating them. The implications are certainly mind-blowing for Mansfield. These aren't even curiosities, they are all parts of a complete system, proof of a civilization that made mathematics an instrument of order. As advanced as any tool used before the Renaissance, the Babylonian scribes were so well equipped and yet ignored by history. Yet, one question still haunted Mansfield. The broken edge of Plimpton 322 is but a silent derision. What might have been carved on the missing columns? Might there be further data, possibly instructions, disclosing the ultimate purpose of this tablet? The remaining rows have already revolutionized the timeline of human knowledge. Should one be able to reconstruct the missing part, one might discover the origin of this system for the Babylonians. One shard still mocked the theory, the missing edge that could prove intent beyond doubt. AI restores the forbidden pattern. For over a century, the broken edge of Plimpton 322 taunted scholars like a riddle missing its last line. Everyone agreed the tablet wasn't complete, but without the missing data, its true scope was speculation. That changed when researchers turned to artificial intelligence. Trained to read ancient cuneiform strokes and cross-check mathematical structures, the AI was tasked with reconstructing what human eyes had not seen in nearly 4 millennia. The results shocked even the experts. The machine didn't just provide hints or vague suggestions, it rebuilt the missing columns with startling clarity. Each number predicted by the algorithm slotted perfectly into the existing sequence, restoring the tablet's logic as though it had never been broken. Suddenly, the progression of Pythagorean triples flowed seamlessly from top to bottom. For the first time, Plimpton 322 could be seen in full, as a mathematically flawless reference table. This statement had ominous implications. The Babylonians were not torturing their imagination with trial and error experiments.
Babylonian surveyors, who have their own unique understanding of right triangles and rectangles,
but practiced an algorithm for whose operation an eerie analogy may now be dragged to modern software written on clay. The numbers logically progressed from steep slopes to shallow ones, producing what could have been an ancient lookup chart. Builders or surveyors could have consulted it functionally, like we open a calculator app now. In another respect, this reconstruction carried a disturbing truth. The Babylonian system was in many ways better than our own. Their base 60 mathematics easily allowed for clean fractions and exact ratios. Our own decimal system falls down when dealing with fractions. No rounding, no approximations, and hence no errors. In some cases, they actually obtained results better than those commonly taught in classes today. The thought that 3,700 years ago, A civilization functioned with a cleaner and more efficient system than we have today was simply eerie. That means we have not simply progressed, we have also regressed. The implications regarding Babylonian culture were equally unsettling, particularly if that table was seen as a baseline. What else might they have computed with equal precision? This was not a case of one-off accuracy. The absence of scribal errors suggests an underlying mathematical culture. It made one wonder if, under Mesopotamian soil, or in some museum, there might exist even more highly sophisticated tablets. Quite what 10 or 20 could reveal to provide insight into mathematical history was rather potent for just 2/3 of the clay artifacts. Scholars were thus forced by the AI results to regard not simply the sophistication of the Babylonians, but why that knowledge was so carefully encoded. The damaged, broken edge, once considered just that, broke open new interpretations suggesting deliberate concealment or removal of vital ingredients. Was the knowledge simply too powerful, too much of a change, to leave whole? Had it been evaluated as dangerous by subsequent generations, with part of it purposely destroyed? One looked at the restored tablet. The more it resembled a skeleton key. Math was not just mere math. It was rather designed action math, which could govern land disputes, guide massive construction projects, or even map the heavens. Completing the missing section may have resurrected an implement that the Babylonians themselves buried for reasons we cannot know. And that was the most terrifying thought of all. Knowledge isn't always lost accidentally. Sometimes it is purposely hidden, for those who once possessed it feared what it could bring forth. A 3700-year-old tablet just reminded us that knowledge can be precise and merciless. If this deep past was running on ratios and rules, what else is still buried in clay and silence? Like, comment, and subscribe if you want more decoded mysteries. Tell us, was this system lost by accident or buried on purpose? And watch the next video on screen for another artifact that refuses to stay quiet.